New topic today, logistic regression. So in our big bestiary of analyses, remember we outlined it kind of like this. We have nominal and continuous x and y variables. And we started out, of course, with ANOVA. We then moved on to regression, and we had ANCOVA most recently, ANCOVA, which contains both nominal and continuous independent variables. And now we're going to move to a continuous x variable with a nominal y variable, and that is called logistic regression. So it's a kind of regression, but the French word logistique is in there. And so what is logistic regression? Logistic regression is when we want to answer questions that obviously have a nominal y variable. And there are a lot of interesting ones in biology where you might have y variables that are nominal. For example, does the expression of gene X affect the possibility of an individual getting cancer? Okay, so we have some gene and we have a continuous variable, the amount of expression of that gene, and that gene might in turn affect whether the individual gets cancer or not, and that's a yes-no kind of dependent variable. We could, there are lots of cancer kinds of examples like that we could use. We could turn to another medical one. Does LDL cholesterol, I just had my cholesterol checked, so I'll bring this one up. Does the LDL cholesterol affect the chance of an individual dying within 10 years? Okay, so what's our x variable? It's LDL cholesterol level, which you can easily measure, and then our y variable is death. Yes or no, the person expires within 10 years. We can move on to more kind of animal ecology. Does the size of a wolf determine the probability of becoming the alpha male? Maybe the size of the pup, right? Does the size of a male pup, a male wolf pup, determine if it becomes the alpha male? It's kind of a cool question. I like wolves. Okay, so let's try another one. So does percent body fat of hibernating bears go into their dens and measure percent body fat of hibernating bears, determine, this would be female bears, whether they have one or two cubs. So our dependent variable is 1 versus 2, and percent body fat is a source of continuous x variable. Boy, we could come up with lots of these, right? And the interesting thing when you think about the biological problems is that dependent variables that are nominal like this are quite common and very interesting to look at. So, I mean, what's more fundamental than survived and died, right, during your experiment, or naturally? What about obtained a disease or not? You got the common cold or didn't get a common cold, got the flu, didn't get the flu. If you're a prey item, you could be eaten. or maybe you weren't eaten. If you're a female, you're reproductive, or maybe you're not reproductive, or maybe you have 1 or 2 offspring or 3 offspring, but you can't have 1.5 offspring, so it's really not a continuous variable, unless, of course, you have maybe up to 10, 12, 14 offspring, then it's effectively continuous. So you can change y into a continuous variable. But if y is just possibly 0, 1, or 2, well, that's kind of a nominal probability. Remaining dormant or becoming active, in the case of organisms with dormancy. So there are lots of very interesting y variables that we want to explain, and often they're functions of continuous x variables, and we want to test those hypotheses with logistic regression. Now, if they're functions of nominal x variables, then we are in that 4th corner that we will look at next, which is a log likelihood kind of test. Okay, so that's where logistic regression fits. So what exactly is logistic regression? In logistic regression, what we do is we perform what's called a logit transformation. And that involves nothing more than, so a logit of y equals the natural log of the probability of something happening over the probability of it not happening. Okay, so P is the probability of outcome 1, and 1 minus P is the probability of the alternative, if we have just 2 possibilities. Okay, so if y is alive or dead, P might be the probability of being alive, and 1 minus P is the probability of dying. Of course, you can always swap it around too. Okay, so what do we do when we fit this? So we fit a function log of P over 1 minus P equals A plus Bx. That looks a lot like logistic regression, right? And this would be the simplest form, where it would be a simplest form, where we're just assuming this linear, log linear function, of course. Of course, we could fit other functions as well. And our null hypothesis would be, what do you think? It would be where b equals 0. So what does this regression curve actually look like? So if we were to plot the log of p over 1 minus p versus x, it would look like that. It would look like that. But that's not really very helpful for us to sort of visualize the function, because again, it's not really, we don't know what the log of the ratio of happening versus not happening, even though it might be linear. That doesn't tell us really what the p, the probability of surviving, for example, is as a function of x. We want to know what this function looks like. So we can solve for that function, no problem. Go ahead and erase that. Natural log of p over 1 minus p equals a plus bx. Then, well, we know what the natural log is. We can use the definition, right? And so then we can have p equals 1 minus p times e to the a plus bx. And we multiply through e to the a plus bx minus p e to the a plus bx. All right, then we can add this to both sides, so we get p plus p e to the a plus bx equals e to the a plus bx. And we factor out p times 1 plus e to the a plus bx equals e to the a plus bx. And we can divide both sides by 1 plus e to the a plus bx. And this is the function, then, that gives you the probability, p, of something happening as a function of x. Of course, now we want to know, what does that actually look like? And, we have to plot it out actually. But it depends whether b is negative or b is positive. But most of these functions are going to look something like this. And that's why they're called the logistic, because they have that kind of shape to them, much like the logistic equation in ecology. Okay. So that logit transformation, when we're kind of back transforming in a way when we're doing that function I just spelled out for you, looks like this. And so our functions will often look like that. And by the way, rarely is it ever reported, this equation. So remember this one, because you can go looking for it and it'll take you a while to find it. But it's very useful to know this, because you can do the logistic regression in SASJump, for example, get your A and your B, and then create an Excel spreadsheet over the range of values that you would typically get for your X variable. You can calculate that probability, and you can actually plot that curve. But and that can be very useful in terms of showing the nature of the relationship between X and Y with logistic regression. And you can even use that function to read off specific values. So if I wanted to know, for some reason, what a given LDL cholesterol meant in terms of probability of dying over the next 10 years, and I knew mine was right there, I could say, well, my probability, my average probability, the expected probability, right, the p hat for this person right here, person x1, would be that. And I could do the same thing for other values of x. Okay, so it can be very useful as a predictive equation for expected values. And of course, individuals vary, right? Some individuals will die, some individuals won't. And also, you always need to remember that when we have one x regressed against one y, there are other factors involved that we don't know about. In other words, there is error. And so it's kind of interesting to kind of look at the data. If you actually plot the points, you might have points that look like this, and yet we're fitting this continuous curve to those points. In fact, over on the left, you see an example of that. If you look over the graph over here, you see an example where the points are over here and the points are up here. So the points are 0 and 1, or whatever the two values happen to be, alive or dead, but we have probabilities being plotted here, and then in between we have some kind of a curve. And so the null hypothesis is that there's no relationship, and we are testing whether, in fact, B, remember this all-important B function, or B coefficient, is what we're interested in, and whether that is significantly different. So we are going to input real data like that into SASJump and get A and B, and we will be able to use this equation to actually plot probability of dying, of having 1 versus 0 offspring. By the way, I just want to mention this right now. In biology, we often run into this problem of we'll have a data set where we have individual 1, 2, 3, 4, 5, 6, 7, 8, etc., right? And we're measuring something like reproduction. And often, a bunch of the individuals are non-reproductive. And then you have reproductive individuals that might have huge numbers of seeds or offspring or whatever, but a lot of them are zeros. And you wonder, how do I analyze these data? I can't transform that to get it normal. What you can do, though, is you can create two variables from this. And you can have one variable be reproductive or not. So you can change all the zeros to not reproductive. And you can change the ones that reproduce to yes. All right, and the ones that didn't reproduce again to no, etc. And then you can analyze this variable with logistic regression. And then you can also, for the reproductive individuals, separately. You can do a separate analysis where you just include reproductive individuals and you put missing data in for these because they're irrelevant. They're not reproductive individuals. And then oftentimes you can do transformations on just the remaining reproductive individuals. So basically what you're doing is you're breaking down the original question, which is, the effect of some x variable on reproduction. You're breaking it down into two parts. One part is, is there an effect of x on whether an individual reproduces or not? And then, is there effect of x if an individual reproduces on the amount of reproduction that occurs? I can't tell you how many times I've done that kind of thing where you're basically changing a single variable into two variables, one of which is nominal, no yes, and the second of which is a continuous variable for which we can use our typical parametric statistics. All right, I hope that was helpful for you, and I'm just going to mention one more thing. Logistic regression isn't used enough. And I'll tell you, it's tempting when you have something like, let's say you're looking at cholesterol level and you are, wanting to know, does that influence death, or whether individuals die or live during some period after you've measured that. Okay, so often what people will do is they will compare the cholesterol levels, dead, alive, and you'll see that, dead individuals, the individuals that died over that period of time had higher cholesterol levels than individuals that lived. So this is fine. I mean, you can do that analysis. There's nothing to say you can't do an ANOVA, right, if you want to, and kind of ask, thinking backwards about this, whether the dead individuals had previously higher cholesterol levels than the individuals that lived through some period of time. That's fine. But it turns cause and effect on its head, right? Because what we're proposing is that this is our x and this is our y. So why not use logistic regression where you have a continuous x and then you have alive dead? Okay, so you have maybe dead is up here and alive is down here, and you're fitting a function to it. And you're pretty certain when you do this that you're actually going to find an effect more easily because you are looking at a continuous variation in this x, right? And the result in the y is nominal. Actually, I haven't done that test, I don't think, very many times. But a very famous biologist I once knew actually did this test when what was on the x-axis was a y variable and what was on the y-axis was really an x variable. And I found that amusing later on. I didn't know about logistic regression at that point in time, and I just thought, well, that's very reasonable, although it seems backwards. And then I later found logistic regression and thought, that's what he should have used in that case. All right. So I'll leave it there. I just want you to know this is a very useful tool for your statistical toolbox. Take it, use it. I think you'll like it. Bye.